So today I'm going to be talking about alkanes, and more specifically I'm going to be looking at how their intermolecular forces exist and how their boiling point, melting point and volatility is affected by their varying intermolecular forces, and why it's affected by their varying intermolecular forces. So to start off, we're just going to have a look at CH4 or methane, which is this first alkane, and we're going to be looking at why it is nonpolar to start off. So the reason it's nonpolar, alright, first of all I'll just go over what it actually is. So it's a carbon atom, which is the middle, the black ball in the middle, and it is covalently bonded to 4 hydrogen atoms. Now, as you know, carbon has a greater electronegativity than hydrogen. This means that the carbon atom is going to be pulling in the electrons in these bonds towards itself. But the reason that it is non-polar, the reason it is not polar, is because this type of molecule is a perfect tetrahedral shape. Now this perfect symmetry cancels out the asymmetry of the electronegativity. So although there's an asymmetry of the electronegativity, the perfect tetrahedral shape, which you can see here, the perfect tetrahedral shape cancels out this asymmetry. And that's the reason all alkanes are nonpolar. So this lets us know that the intermolecular forces between alkane molecules have to be London dispersion forces, or which are also known as van der Waals. And the way these dispersion forces work is each atom has an electron cloud, and then the molecule itself has an overall electron cloud. So if you imagine that this electron cloud looks roughly like this circle. So this electron cloud, it can move around. It can be there. It can move around to be like this. So it varies because the electrons can move. It varies exactly its shape. So if you get a scenario where it looks like this, you're gonna end up with one side of the molecule being very or slightly negative, and one side being in turn slightly positive. This here is called a momentary dipole, and this is how the London dispersion forces work. So once one molecule creates a momentary dipole, it affects other molecules. So if a molecule with a momentary dipole comes across a molecule with that doesn't have a momentary dipole, it's going to alter its electron cloud, and it's going to also make it skew, because we know that electrons repel each other. Well, positive repels positive if it's on that side of the molecule, and negative repels negative if it's on that side. So it's going to make molecules around it skew. These molecules that it makes skew is called induced dipoles. And the interaction between momentary dipoles and induced dipoles is what a London dispersion force is. So that is that force. And in knowing this, we can determine that the electrons are the things that, make these forces. So if a molecule has more electrons in it, these forces are going to be stronger, because you're going to be getting more, one side's going to become more negative and one side's going to in turn become more positive. It's going to be stronger positive and negative points on the molecule. So this becomes really important because from there we can look at, well, methane is obviously going to have less electrons than ethane, and it's going to have a lot less than octane, which has 82 electrons. So this means that octane is going to have far stronger intermolecular forces than methane. And this is really important because in knowing that octane's going to have far stronger intermolecular forces, we can also determine the relationship. We can also determine that it's going to have a greater boiling point than methane. So its boiling point is going to be higher than methane's. And the reason for this is to break the bonds, which are the London dispersion forces, so the bonds between molecules. It requires a lot more energy to break the bonds between octane molecules than it does to break the bonds between methane molecules. Because as you know, as we just covered, the dispersion forces for octane are far stronger than the dispersion forces for methane. And you'll find it's the same thing for melting point too. So in knowing that the bonds for octane are far harder to break than the bonds for methane, we can also determine that methane is going to be far more volatile than octane. And you'll find, as we go up the alkanes, the volatility in this case, in this scenario, is going to decrease. It's going to decrease because, as you can see, there is more atoms in these. And more atoms means more electrons, and more electrons means stronger London dispersion forces. Now it's also going to decrease because more atoms means more mass, which is another factor that affects the dispersion forces, and in turn affects the boiling point, melting point, and volatility. So octane is going to be the least volatile, and going down, it's going to get more and more volatile until you get to methane, which is going to be the most volatile. So it can change phase the easiest. So methane is going to have to be stored in extremely controlled environments. These environments, compared to octane, are going to have to be controlled heaps more. To keep it in a liquid state, the environment is going to have to be cold, like extremely cold, 24/7, and that's going to have to be monitored. And in case the temperature does change, there's going to have to be valves in the storage tank, and these valves are for releasing pressure in the event that the temperature does change, and because of how volatile it is, the event that the methane does expand. And it's the same story for ethane too. But if we go up to butane and propane, so these are the gases that you use at home to cook stuff up on the gas stove. So they're going to have to be stored in tanks, and they're going to have to be regularly checked, and usually the tanks are put in a cool area. They're painted a colour that responds well to the sun, so it doesn't take in a lot of heat. So they're going to be painted white or grey, pretty much. That's the only colours you'll ever see. And they're going to have to be checked heaps. But they're still, as I said, they're still not as volatile as methane or ethane. They don't have to be as controlled. And then you get to octane, which you'll find is in petroleum. So petroleum uses it's a mixture of various hydrocarbons, but octane is one of the main ones. And octane is it's flammable. Uh, all of these hydrocarbons you see are flammable, and it's stored in large tanks, and these tanks are earthed because you don't want an electricity. So earthed means it's has well, actually, the tanks above ground are earthed, but they're rarely above ground. Generally speaking, they're underground. And the reason they're underground is one, to protect it from things like lightning strikes, because you don't want a lightning strike to be hitting a extremely flammable tank. And the other reason is to keep it cool. But it's it's petrol. It's what you put in your car. So it's not as volatile. And the reason the reason you can do this is I go into more detail with this in the document, but it has a relatively high flash point, so it's for that reason it's pretty safe to handle, and its high flash point is due to its dispersion forces, which we covered today. So yeah, that pretty much covers the dispersion forces part. And to just take a look at these molecules, sorry, these models of these molecules, they have their limitations um because they don't really give you a good idea of how many electrons are here. They don't show the electron clouds. I can move them, but they don't. It's not the it's not the easiest thing to understand. But the good thing about these molecules is they are all. So this is a perfect tetrahedral shape because I've generated it with a CAD software. There's no there's no room for human error here. It is a perfect tetrahedral shape. So that's a good thing about these molecules, is they're all accurate in that way. But yeah, they don't show the electron clouds. They don't show the dispersion forces. So models that could show that would be a lot more effective in explaining this.